Welcome to a presentation about structural analysis of major Formula Student racecar components at TU Wien Racing. Today we are going to present you 3 different simulations we have performed with Altair software to make our car faster. My name is Philipp. I'm part of TU Wien Racing since 2018 and I've worked there in the chassis and composite department doing implicit and explicit analysis. Right now I'm focused on crash simulations using Altair's explicit solver Radius, and besides TU Wien Racing I'm studying mechanical engineering at Vienna University of Technologies and have worked as a design engineer for a couple of years. TU Wien Racing is a 2006 founded Formula student team based in Vienna. Since the year 2013 we're building electric race cars, with which we are competing at Formula student events all over Europe. Our philosophy is to find the lightest possible solution, and that's the reason why nearly everything on our car is developed by ourselves. For example, our self-developed powertrain, so the electric motors, inverter, gearbox and also the battery pack are all designed and analyzed by our engineers here in Vienna. To achieve the lightest, stiffest, or most efficient design in nearly every component, we perform a lot of analysis and optimizations during a racing season. For example, we use OptiStruct and Radius for structural analysis, or Inspire to create the next generation additive manufactured suspension component. To speed up our overall development process by reducing physical material testing time, we just started to use the multi-scale designer and do more and more material testing virtually, which is great. And regarding the electromagnetic simulations, we do those in flux to see how the magnetic fields in our self-developed motor spread. And last but not least, our vehicle dynamics department uses chassis sim to tell us what actually makes our car faster around the track. But for today's session, we will focus on structural analysis performed with OptiStruct. And for now, I will hand over the presentation to my colleague Rudolf, who will start with introducing you into a drivetrain simulation.
Hello and welcome to my presentation. In this session, we are going to talk about an analysis of a drivetrain assembly. We will use HyperWorks meshing tools for the mesh generation and optimization. We will talk about the contact analysis setup, and we will also take a look at nonlinear pretension analysis and using subload cases. My name is Rudolf. I'm studying mechanical engineering at the Vienna University of Technology. About my past in our team, from 2018 to 2019, I was a team member at TU Wien Racing. The following year, I was in charge of our team as the Chief Technology Officer. And from 2020 to today, I serve as the head of electric machines and as a member of suspension. My main responsibilities are the development of our motor, drivetrain, and wheel assembly. So what are we using this simulation for? First of all, we want to make an estimate on how the assembly deforms under load. So we want to make a stiffness evaluation. Secondly, we are always looking for opportunities for rate reduction. And last but not least, the displacement of our gearing components directly affects the gear meshing. So we want to calculate the exact displacements of our gears in order to later on compensate for that. Here's our quick overview of our CAD model. On the left, you can see the motor with our upright and the wheel hub attached to it. On the right, you can see a cross-section of our assembly, including the contact patch center point, which is here, at which we are going to apply the loads in the Y and the Z direction. Keep in mind that we are not going to simulate the tire and the rim itself, because that would increase simulation complexity a lot. And we are only going to use the rigid connection from the center point to the wheel hub itself. Taking a closer look at the wheel hub and drivetrain assembly, first of all, we are working with a planetary gear train design. So you can see the sun gear in the middle the first and second stage of our planet and our ring gear. In addition to that, we're using angular contact bearings. So in red, you can see the contact angle of both our bearings and the intersection with the center line. So at those points, we're going to constrain our model with rigids connected from here to the contact area of our bearings. In addition to that, we are going to apply tangential and radial forces at first and second stage of our gearing. Before we can start meshing our geometry, we first of all have to simplify our CAD model and remove any unnecessary geometries that are not necessary for the simulation and are not in critical areas. So we remove unnecessary bars, chamfers, or fillets that might interfere with meshing the geometry later. Regarding meshing itself, for the more complex shapes, we are using 3D tetra mesh. And for other rotational symmetric parts like the pin shafts, we're using hex elements. Reason for that is for the more complex parts, it's often more time efficient to make a tetra mesh. In addition to that, we are using 2D support meshes that you can see in blue that we are using in local areas that we are either more interested in or we want to have more control over the mesh in certain areas. And of course, as usual, the usual rules for discretization and meshing apply. We also use the solid mesh optimization tool, in which you can define your required quality metrics of your mesh. You can check your elements for them, and if you have elements that do not meet those requirements, you can also use the fix function to make it automatically fix those elements if possible. Regarding contact definition, we first of all assume that we have a fully meshed geometry. And as we are dealing with 3D elements, we have to do a bit of a workaround for element selection. So first of all, we create a new 2D mesh using the function faces, which exactly matches our 3D mesh. The reason for that is that we can then select our elements that we want to select, first of all in the 2D mesh. Then we go over, we show the 3D mesh, and then we again select our elements by adjacent. This will then select the adjacent 3D elements from the selected 2D elements. And then we can create the contact group, select the respective element sets, and define a contact behavior. It is advantageous to stick to a human-readable naming convention when dealing with your contact sets. This will make things a bit easier, especially when dealing with larger models with many different sets. It is also a good idea to always check your contact sets accordingly, so you make sure that you selected the right elements that you want. Regarding your pretension definition, we again assume that we have a fully meshed geometry. And with using pretension, we can either use 1D or 3D bolt elements between selected nodes. In our case, we are using 1D C-rod elements between two rigid nodes. Under Analyze and Bolt Pretension, we can open the Pretension Manager, create a new load case, and select our bolt elements. So we select the bolt elements that we want to pretension. We create a new load collector that we call Pretens1, and we also define the magnitude of our pretension, in this case 4000 newtons per bolt. Following that, we create a new load step, which we call load step pretension, which is a nonlinear static load step in addition to the already existing external load step, in which the external load is applied to the tire. For that itself, we need to create some load step input cards called NL_parent, NL_adapt, and NL_out, which we first have to define. And then under the load step pretension, we can select those input cards, as well as the constraints that we defined earlier. And also under pretense, we select our pretense load case that we defined in the pretension manager. Lastly, when creating our external load step, we select our constraints and our loads as usual. In addition to that, under stat sub, we have to select our pretension load step. So when the solver solves our model, the pretension load step gets solved first, and the results from this load step will be then used as a starting point of our second load step. So this will take our pretension into account, and then we'll apply the loads externally. Thank you very much for your attention, and let me know if you have any questions.
Hello, and welcome back from my side. Now we're going to take a closer look at a simulation very relevant to our suspension department. I'm talking about linear buckling analysis of our fully laminated carbon fiber wishbones. During the development process of our wishbones, we do multiple implicit analysis with OptiStruct, and for this session right now, we're going to focus on the stability failure resulting in buckling of those hollow wishbones. And the key step here is the combination of a linear static and linear buckling load step, which is needed to perform a linear buckling analysis. Right in the development process and during the finalization of the ply layup, we had some initial simulations running and performed physical testing with prototype wishbones. During those tests, we saw that buckling is an issue, and our critical failure modes were compression and buckling. And based on those results, we decided to further develop our simulation with a new focus on those critical failure modes to be able to develop a new ply layup, and we also adapted our choice of materials. To set up such a complex simulation, we do prefer to do very small steps, so start with a very simple model and add complexity with each step. So we started with an isotropic tube. In the next step, we changed the isotropic material into a Mat8 carbon fiber material, and just after that, focus on the wishbone itself. As mentioned before, in the linear buckling analysis, we need two load steps. First of all, we define a reference load, Pref, which is used in a linear static load step to calculate displacement, stresses, and strains, which are then used in a linear buckling load steps, which the linear buckling load steps is all about solving an eigenvalue problem, which gets you the critical loads and the certain buckling modes happening there. To provide the input data for the linear buckling load step, we need to define an IGRL card, which is basically about what eigenvalues you want to calculate. And now let me just jump into my HyperWorks. Here we can see the carbon fiber tube. So the meshing, the properties, the materials is already done. We just have to look at our load steps. Here is our tube. We see our constraints, our loads. They are here. Yeah, the SPC, the force, all right. And also down there. That's good. Great. So have a look at the load step. We already have one defined here. That's our linear static load step. So for the linear buckling load step, we need to define our card first. So that's done by using the load step input. It's already popping up. So we're defining our eigenvalues, range of interest here. Should be fine, frequencies. Buckling. That's done. And now we can define our load step. Which is about linear buckling. We need to choose the right analyze type. Linear buckling, alright. For the stat sub, we have our initial, our linear static load step, of course, and the method is here, our already defined card. And now the model should be ready to calculate. That's all it takes. And I'm switching back to my presentation. Looking at our final model, we tried to model the physical testing as precisely as possible. Regarding the wishbone itself, such a great level of detail meant to to model the carbon fiber structure of the wishbone, the inserts, and even the ball joint very precisely. In the composite menu you can see all the different materials we have used for the simulation, and I've been talking about the physical testing. That testing was used to, on the one hand, validate our simulation, and on the other hand to calibrate our strain gauges, which are mounted on the wishbone, on our final wishbones. Overall, for the modeling, we used a second order combination of quads and trias. For the laminate, we used the ply-based modeling approach, so P-comp-P property with MAT8 material card, and for inserts test devices we used a three-dimensional mesh with a MAT1 material, and the stacked areas of the wishbone, so the fully solid carbon fiber areas around the uniball where the ball joint sits, also uses a three-dimensional mesh with a MAT9 orthotropic material card. The ball joint is modeled with a 1D joint element, in this case the FE ball, which is connected with a combination of RB2 and RB3 elements to our outer ball joint housing and the bolt of our test device. And as mentioned before, the stacked carbon fibers, so fully solid carbon fiber area, the purple ring you can see in the picture below, is modeled with a three-dimensional mesh and is connected via a contact to the rest of the laminate. Looking at our results of the linear static load case, in this case the composite failure index, which is for the whole structure below 1, which is good and tells us that our laminate is not likely to fail. We used the Tsai-Wu failure theory, which can be chosen in the P-comp-P property card, and looking at the linear buckling analysis, you get your different buckling modes at your different loads, and you need to investigate what buckling modes and, in further case, what critical loads are you need to consider in your application. Because if you look at our wishbone here, we have two arms of the wishbone. One arm is fixed into the test machine, so both ends are constrained. But the other arm, one arm is not constrained, so this end is allowed to move, and we should not consider that in our buckling analysis. So we need to find the buckling modes are relevant to our application and define the critical loads after that. In the end, we were able to predict the global buckling failure of our prototype wishbones quite precisely. And with that simulation, we were able to define our new ply loop and also took a look at the local buckling modes and took those into consideration at developing the new layup. With our final wishbones, we were able to achieve a difference in stiffness regarding simulation and physical testing of less than 10%. So at that point, the simulation fulfilled all initial goals, and the wishbone was further evaluated in an assembly simulation. So that's it from the wishbone development. I have to thank you for your attention, and I hand over the presentation to my colleague Martin.
Hi and welcome to the last part of our presentation. My name is Martin Molnar. I study mechanical engineering at Vienna University of Technology. I joined TU Wien Racing back in 2018 as member of Composites. Then I became head of chassis, and since 2019 I'm member of chassis and composites development. I'm currently working on the suspension pickup points. And today I will be talking about sandwich structure and specifically about 3-point bending. Inform a student, we have some rules regarding structural integrity, equivalency, which leads to driver safety. So we need to split up the monocoque in different parts and make some physical tests to pass this document. And for this reason, we use HyperWorks OptiStruct to simulate the panels before we could test them. But first, we start with with a calculation to get an idea about the material behavior and the stiffness of the structure itself. Then we make some basic simulations, and to get the right ply layup, then we do physical testing, and if the test panels pass this document, then they build the base layup of the monocoque. But we also use the data from physical testing to refine the boundary condition, and also for more complex simulations where we model the sandwich structure itself, and also the suspension pickup points, the inserts, and the splice adhesive. With this data, we then can improve on performance globally and locally. But today, I will be concentrating on ply-based basic simulation, and at the end I will compare the results from this simulation to physical testing, and also to calculation and modeling the sandwich structure as well. So first of all, I will show you how to set up a basic ply-based simulation for 3-point bending, where the sandwich structure is modeled as a ply. So the panel which is to be simulated is 275 by 500 millimeters, and the force acting on it is around 8 kilonewtons. Here you can see the material data used for this simulation. If you want to make the simulation yourself, then use the data in this picture. Then a short tutorial about the basic simulation. So first of all, we need to create a surface that we can mesh afterwards. It's 500 by 275 millimeters. Then we create the mesh on the surface. For the beginning I did a 5 millimeter mesh. Then you need to check for the element normals, if they are all showing in the same direction, and also the material orientation, which is very important, that all the elements look in the same direction. If it's not the case, then you can adjust it by a vector, which you then project to the elements, so that all the elements look in the same direction. Then you can define the materials given in the presentation for this simulation. We are gonna use 3 different materials, one unidirectional, one cloth, and one core. The core is an aluminium honeycomb with 40 millimeter height, and after we finish defining the materials, we can start with the composite itself. But before that, let us make the test rig, the coordinates, the nodes for the test rig, and then we can start with the plies. As you can see, I define 3 plies, one in 45 degrees, one in 0, the unidirectional, and one in minus 45 degrees. Then I define the core, but we are going to use the symmetry of this layup, so the core is half as thick as it needs to be, so that after applying a symmetry to the laminate itself, it has the right thickness. Now laminate you can make under composites, and then drag and drop the plies to the right laminate. Then you also need to add the property, a composites property for this. I use the P card, and here you can check for the right thickness. It's a representation of the panel, and after you check if everything's correct, just add another component, rigid, where we define the test rig itself. It's very useful to have RB2 elements for this setup, because you can adjust the degree of freedoms of every node vertically. Then you can also add your load collectors for the single point constraints, and also for the load. The load, as I already mentioned, is around 8 kilonewtons, and this node must only move into one direction, downwards, minus Z direction. Then you can also refine the degree of freedoms of the rigids and also the SPCs down there. So after everything is defined, you can define your load step, the load step, and start your simulation. For the simulation, for the results, I used a different model. The model I use for the results is more refined and has a finer mesh. And as you can see, the result is around 12mm displacement. And in HyperWorks 2021, you can also look at the displacement and stresses directly in HyperWorks itself, so you don't need to open HyperView. You don't necessarily need to open HyperView, and it's very good. And it's also very good to look at the deformed state of the simulation as well, so that you can check for any error in the boundary conditions as well. But why are we doing a simulation like that if we could also just use ASAComp and do the calculation or the simulation in there? We use it to set the boundary conditions right and to get an idea about the structure itself. And with the knowledge we gathered from this basic simulation, we head over to a more specific simulation where the core is modeled as well. And here, as you can see, we start with basic boundary conditions, and then we get over to more detailed simulation where the testing rig is modeled as well. And with this data, we can then model and simulate the suspension pickup points as well. But not at least, a comparison of different methods, and the calculation and ply-based simulations are a bit more stiff than the physical test, but you can see a good correlation in between the ply-based simulation and physical test already, and we could further improve the correlation between the modeled core and physical testing. Keep in mind that the testing rig has also a stiffness, so that the results from the tests aren't necessarily the results that you are looking for. You need to subtract the stiffness of the testing rig from the results as well. And at this point, I want to thank Altair in name of TU Wien Racing for the support and for their products, and we are happy to answer your questions.